Yeah, that's a surprise. We still have many people, so that's great. So yeah, so it is my pleasure to introduce our speaker, Yiqiao from Schlumberger-Doll Research in Cambridge, just near us, like a 5 or 10 to 10 minutes by walk. And Yiqiao also worked at the Martineau Center of Biomedical Imaging of Mass General Hospital. And his research involves development of nuclear magnetic and imaging techniques and instrumentation to understand complex materials and fluids. His interest focuses on the physics of diffusion dynamics in porous media and biological tissues, and the development of multidimensional experimental methods and numerical invariant algorithms. So these multidimensional experiments have been broadly used in research and industrial applications. One of his current areas of interest is the Bayesian theory, uncertainty, and machine learning as a means to optimize NMR, MRI, NQR data acquisition in real time in order to enhance the speed and quality of the experiments, and for robust automatic applications. He is a fellow of American Physical Society and a member of the editorial boards of Journal of Magnetic Resonance and the Chinese Journal of Magnetic Resonance. So yeah, so let's join me to welcome Yiqiao to give the talk.
Thank you very much, Chan, for the introduction. I was telling some of your colleagues that I came here quite a while ago and give a talk, but I don't even remember where I was, whether in this building or somewhere else. But anyway, so what I want to talk to you about are the connection between two topics. One is, of course, the rock that must be familiar to this audience, and the other is probably a little less familiar. That's using magnetic resonance technique to understand various aspects of rock. And today, I want to focus on not generic understanding of rock, but more of the chemical analysis of, in particular, the organic materials in various rock material. Again, this audience, everything that's shown here. Rocks is very important, and also is complicated in many ways. In particular, of course, the geology focuses on the evolution, the sedimentation of the geological material. And on the more practical side, people look at the pore structures and from the point of view of extracting the fluid in the porous material. And people have talked about energy. Certainly, a lot of the energy comes from the subsurface rock formation. I would say even in the new era where renewables are going to be increasingly more and more important in the consumption of energy and providing the energy, but still, hydrocarbons for many years will still be the major source of energy, and then so the continuous exploration and production of energy from geological formation remains very, very important in a sense for the entire globe. Of course, the rock is complicated, as I said earlier. There are many particular issues I just want to point out, and everybody knows about this. For particular, and not only you have these aggregation of grains that generate pores, but also you have clay minerals that provides a particular type of pore system, for example, with much smaller pores, and they have their own issues that complicates the characterization of rocks. And if you look at the larger scale, of course, the levels of complexity, in the pore space, you can go on, and that would be an entirely different talk. I think we actually recently have some new work that allow us to move beyond the very simple models of capillaries and then go into much more complex pore body, pore throat, and these more detailed structures. So hopefully, I'll find another time to come to talk to you about some of the more recent work. But today I wanted to talk about the materials that's in the pore space, right? Of course, the material that we are interested in from an energy perspective are these oils that reside in the pore space, and some of the field have light oil and heavier oils, and all the way up to the very heavy organic materials. And if you have paid attention to okay, so in the recent, let's say, recent 10, 20 years or so, especially in U.S., the unconventional oil has become a very significant production of oils in U.S. in particular. And these type of rock give you not only the grains and not only the ones that we all know in the more conventional reservoir, but they have significant amount of solid organic materials. For example, this is a picture, microscopy of a piece of rock with the solid organic material called the kerogen. I mean, you can talk about their porosities in the kerogen and everything, but these kerogens contribute to the flow problem in a very different way, right? The kerogen is very viscous, and they're not going to flow, right? So even though they are organic materials, but that's not the organic materials that an oil field will produce. So in some sense, their impact on the fluid flow is non-trivial. And in fact, if you look at all of the fluid, let's say, in a rock material, right? You have many different kinds, as we just said. You could have these organic solid, and you could have these things that are called bitumen. They are just very heavy hydrocarbons, for example. And then you certainly have oils. That some of it is free to flow, or I mean they're in the large pore, they can flow very well. Or some of them are in smaller pores that have been held by capillary pressure, capillary forces, and they may not flow. And of course, you have clay, you have waters, and so as from a practical perspective of someone to characterize a piece of rock and then to tell the oil company whether this is a formation that worthwhile to produce or not, and these are all complicated because they contribute to the flow in a very different way. Some are positive, some are negative. Those are not easy to identify. In the laboratory, there are plenty of standard techniques that we can use to figure out what are these different components. But you can only do it when you can extract samples. Very limited analysis you can do. So what we want to develop are the techniques that we can use to translate down into the downhole measurement so that we can measure the entire reservoir, right? So the nuclear magnetic resonance is one of those techniques that detects all of these fluid, and it has a property that can differentiate the different type of fluid, water, oil, and these things that become useful. So today I will talk to you about how we are using magnetic resonance in these kind of scenarios, right? So a few words about the fundamentals. I mean, anybody have some in every episode. MRI is actually quite simple. The name is magnetic resonance, so you got the magnetic part. So this is when a nuclei under some magnetic field, these nuclei, if they have a spin in them, then the spin up and spin down relative to the magnetic field will have different energy, and these different energy defines a two-level system, and they will absorb EM wave or radiate EM wave. That's the signal that we see. So roughly speaking, think about an NMR as you have a magnetic field and you have a big magnetic moment. That's like your little magnet that spins around in the magnetic field, and that's the property we're measuring. And in fact, since we're talking about hydrogen, then all of these formation fluid, like water, oil, they have hydrogen in them, so that's why the NMR detects these fluid. Of course, we know everything. I mean, MRI is actually quite popular in our medical sciences. It's very, very useful in studying human and also detecting diseases and mostly being used in the hospital. But the one thing that is very limiting is that you have to put your sample, like a person, inside the big MRI machine. So for geological work, I mean, it's a little hard, right? We cannot always take samples and put it in a machine. So the work that for geological work, we typically drill a well bore and put instrument on the inside of that well bore and have that instrument be able to detect outside the instrument. So for resistivity measurement, you all know how to do it. It's all kind of natural. But for MRI, it was quite an interesting development. This is done 20 or 30 years ago that people figured out how to do this measurement, where you have your instrument on the inside and measurement on the outside. So the basic structure of these devices are a cross-section, have magnets that are magnetized outward, right? It generates a magnetic field spot over here so that you have a antenna that focuses on that spot so that you can do NMR or MRI outside. So this brown line display let's say the borehole, right? Then the sensitivity spot is information. So this is how you can do NMR or MRI in an inside-out geometry, allow you to probe the formation. And overall, of course, this is only talking about the NMR2 sensor, and that would be here, and then you certainly have a lot of electronics that you have to package into the logging system. So in order to do measurement, so that's your equipment, and similar to when you work in the lab, you have a lab. For people who go out and do these logging measurements, the lab is your truck, right? Your truck has all your power supplies, electronic computers, and also telemetry that you talk to your office and get updates. And in addition to being in a good lab and nice campus like MIT and Cambridge, this is the kind of environment that some of our people worked in. Certainly, work on a drilling platform is pretty tough, but you could also be in the jungle and you're just yourself with the equipment, but you have to get it working. It's a pretty tough environment for compared to a nice setup that you have here in Cambridge, but it also is very exciting, right? This is tremendously well. I would say it's an adventure, right? This is extremely challenging, but you got a lot of stories you can tell. Well, I don't know, Doug, have you?
Am I right? Is that a seismic job, and that's a rig-based air gun?
You mean this?
No, up in the upper right.
I don't know about that. That is just a picture from the Google picture. This,
I'm just guessing that that's
this is a drilling.
An air gun going up, but I could be completely wrong.
Oh no, this must be a
blowing up or anything.
This must be a testing, right? When you pump out the oil, and you always end up with a lot of gas.
Oh,
so that you have to vent that when you have to burn out that gas. So a little bit about an NMR. We would talk about you have these hydrogen molecules, hydrogen atoms in the sample, so that we can detect signal. But when you put the sample into the magnet, right, into a magnetic field, the magnetization grows, right? Grows over time. It's not growing instantaneously. It grows over time. And this process, we call it relaxation, right? This is when the signal, when the magnetization grows along the magnetic field, right? There's a time constant to it. We call it T1. Very smart. We call it T1. And then also, the magnetic moment could be in a different orientation. It could be transverse to the applied magnetic field, and the relaxation in that process is a little different. We call it T2. And this is actually turned out to be important in a little bit later. So in order to measure this T2, we use a series of RF pulses. We don't worry about the details of the pulses, but these pulses, they will rotate the magnetization by some number of degrees. Right? You have two types of pulses. One is 90-degree pulse that rotate this magnetization to 90 degrees, right? It becomes transverse. And these guys rotated 180 degrees. And this 180 degrees rotation is actually quite useful. If you get down on papers and put in rotation matrices for 180 degrees, very quickly you'll find out these 180-degree rotation correspond to time reversals of the Hamiltonian. And that is very important. I'll show you a simple example of why that time reversal is useful. So this is a mechanical example, or an analogy of what these 180-degree pulses do. Is it not going? Okay. It's a little video that I find on the internet.
Okay.
Certainly it's not because somebody learned NMR out of this. This is for a high school student, just try to play with how fluid mixes. But it's actually quite interesting. You put in 3 dots of different colored fluid in a very viscous, let's see if I can get it go a little faster. Well, anyway. So they're in a very viscous fluid, so that they don't diffuse, right? They just stay there. And this container has, so this fluid is in between 2 walls. One is the outside, and then there is a rotating cylinder on the inside. So later in the video, you will show that it will rotate the cylinder. So the fluid will move the dye in a different way, right? So, and then very quickly you will see the mixing. So in some sense, these are signals. When you mix them up, you couldn't tell the 3 different colors, right? That's like your signal is gone in some sense. And notice that at some point, this person just reversed the rotation. That's like our 180-degree pulse. They reverse the time axis. Has he reversed yet? Or no, still going? So by this time it's really, you feel that it's really, really mixed, random and so on and stuff. But in fact, he rotates back and then it gradually unfolds. It ended up to come back almost to the exact initial condition. It was actually quite amazing. This simple mechanical demonstration shows pretty much the same thing as an MRI, which do by these 180-degree pulses. Just you see it's coming back. You can tell that. So this is in the NMR language, we call these spin echoes. And the signal comes back, right? So that's all the fun for today.
The dyes are distinguished by the
Code. Sorry?
Are the dyes distinguished by molecular size? Or
Well, they're different
what
dyes,
property
different
is
molecules.
being distinguished?
You mean different colors?
I see that they're different color, but I suspect that they are moving the way they're moving, not because of being different color, but because of being different chemically.
No,
No,
when you
morphological.
put it in there, they're just in different spots. They're being dragged by the fluid. So it means that even though they look like mixed, but they're actually not mixed. If you follow the flow line, they will all come. If you reverse it will all come back. Yes?
Yeah, I just have a quick comment. This experiment credited to G.I. Taylor in 1957.
Is that right? He made that?
He
Called
proved
Taylor-
the
Taylor-
same thing
yeah, called
as
Taylor
the
Call.
same thing under
Called
the-
Taylor Call.
Actually, it's a series of fluid dynamics and kind of videotaped by them. This is kind of they make the motion picture.
I see,
This
I see.
about these, and
Right.
it's done by G.I. Taylor himself.
I would assume he was trying to demonstrate the dispersion process or
Yeah,
something.
It formed bands called Taylor.
I see. Yeah, well, it's actually quite fun. This is actually, I find it very fun, and when I explain NMR to people, and people are more interested in this than the NMR. It is very true. I'll look it up. I actually don't know that, but I'll look it up.
You can find it even from the web. And
I see. Okay. So in the well, we're talking about NMR. So the NMR the relaxation rate, as we were talking about, has contributions from the bulk property, right? It's dependent on different molecules, that property is different. But also, when it's in the rock, it also measures the surface volume ratio of the pore. That is because when the molecule touches the pore, it experiences a different interaction and it relaxes typically faster. So that's how NMR is used to measure pore sizes. But I promise you, I will not talk about that, right? We'll not talk about the pore sizes. So forget about these things. And then we're talking about more of the molecular property of the different fluid. But we'll find another time to talk about it. At the same time, that if you do the measurement, this relaxation often shows a multimodal behavior. So it's not a single composition. And for crude oil, we all understand, the crude oil has a range of small molecule, big molecules, there's a whole range. So this is the background I want to emphasize, that when we measure something, it's always a big distribution. And it's typically from the molecular composition, and sometimes it's because of the pore size that it has a wide range. And that is a lot of challenge from an interpretation point of view, because when you see something and there's a lot of questions, it doesn't really tell you what molecule it is. So this is one example that I always like to show. This is actually a recent, well, not recent, probably several years ago, a logging example of some wells in North America. So this is, I'll show you what this means. This is a NMR measurement measuring T2. And remember, that was the transverse relaxation time that tells you about the property of the fluid. And vertically, it's a depth, right? So this is a typical log. And on this side is a short relaxation time. This is long relaxation time. So typically, the long relaxation time means two things. One of the two things. Either it's a very light oil, the molecules are small, the relaxation time is long, or they're water in a very large pore. But just looking at this data, I mean, you don't really know. You cannot tell.
And the display itself is intensity of response at that T2 time.
Yes.
So it counts on something.
Right. It's like a count. So of course, every row is a T2 measurement, and just stack them all up. So you see a lot of very short ones. They're likely to be the shale layers. They don't have anything. You don't want them. So it's these signals that you're interested. You say, is it an actual reservoir? Well, from here, as I said, it's either oil or water. You don't really know. So this particular experiment wouldn't tell you that. So you do something else, right? So this is another type of experiment. Sorry.
If you have multiple peaks in the intensity, does that imply a mixture of fluids?
You can, yeah. Mixture of fluid or a range of pore sizes, right? So you have always this ambiguity. So from that T2 measurement by itself, you wouldn't be able to tell. So that's why we are doing this type of experiment. You can see that here is a line, right? So here, my data become a two-dimensional map. Did you raise your hand?
Yeah, the bullseye is an artifact. It's something to be interpreted clearly. The bullseye up in the upper left-hand corner.
You mean this?
No, the one that isn't.
Oh, this
circled.
one.
Yes, the one that circles itself as though it is an artifact of the geometry, an artifact of the way things are being processed.
I honestly don't know, but these are many different data sets. It looks like that. I don't think the way I look at it is all short. It's whatever it is it's short. The T2 is very short. It means it's very heavy or clay-bound water. So we're not interested in that anyway.
But you don't have a story about.
We don't have a story about
thing that the ultrasonic skies would call a galaxy pattern if it showed up in their images.
We need some cool name like that too. So this is actually quite interesting because the water and oil behave very differently on that map. If you only look at the T2, which is this axis, imagine yourself looking up from here. Whether this spot is here or here, you can't tell. You don't know. But when we add this dimension, this is the diffusion dimension, then you suddenly can tell these differences between the oil and water. And why the oil fall onto this line is because if the oil has small molecules, or lighter oil, then it tends to go to longer T2, and also it diffuses fast. The T2 and diffusion are correlated. And if it's a heavier or larger molecule, then the T2 will be short and diffusion will be slow. So the simple relationship between T2 and diffusion allows you to identify everything along here is oil and everything along that horizontal line is water. So this is turned out to be a very useful approach to separate out oil and water. And experimentally is quite different from our traditional measurement. What I showed you earlier, when we measure the transverse relaxation, that we have, this is the experimental protocol that gets you signal here and here. And we added another section, so we call this time period to be T1. So this period allows you to measure the longitudinal relaxation time. And so this whole thing become a correlation experiment. It's become from a one-dimensional experiment into a two-dimensional experiment. So your data is not just a series of numbers, it's a two-dimensional map of the original data, and then you invert it into the two-dimensional map of the in the result. And there's many different styles of these two-dimensional maps. You can measure different properties, T1 and T2. We'll come back to that later. And this is the diffusion, T2. And you say, why stop at 2 dimension? Why don't we do 3? Of course, we do 3 dimensions typically these days in the standard measurement. That you measure, there's a T1 dimension here, there's a T2 dimension here, there's a diffusion dimension. So at the end, your data is larger, and then you can once you do this experiment, you can interpret various results in any of the dimensions that will help you, right? So this is the measurement on our logging tool that of the same example as I showed you earlier. So this also is consistent that the log down hole measurement also show the signal is oil. And well, if you look in details, this is actually a little longer time. Longer relaxation time means that the downhole temperature is a little higher, so the viscosity is a little lighter. And we can also take that, go one more step into a much more quantitative interpretation. Instead of saying this is oil, this is water, we will say what kind of composition in the oil, right? So we know the oil has a range of molecules in them. We can use this technique to actually be much more quantitative. So this is a diffusion distribution. So higher diffusion constant, smaller molecule, lower diffusion constant, larger molecule. You can take the diffusion constant and calculate what is the molecular weight distribution. The dots are measured by gas chromatography, which is a standard approach to measure the oil composition. You can see from the NMR measurement they are quite close. They're not exactly the same, but they're quite close. And the theory goes behind, I wouldn't have time to talk about it. In general, the diffusion constant of a component in a mixture, right, you can write it down as part of its own molecular weight, but has another factor that is the average. That's like the environment, the viscosity of the fluid that affects the diffusion constant. So this is actually quite interesting, a lot of interesting physics in that. And this, you can apply it. You don't just do it in the lab. You can actually do the diffusion measurement in the wellbore and then calculate what molecular size you got. So this is one example in North Sea that we did these diffusion measurement, and this is at a shallower depth of investigation, like 1.5 inches into the formation, and the other track is 4 inches into the formation. So these white lines are the average molecular weight, and these two lines, the red lines and the blue line, the red line is the molecular weight of the native fluid. The blue is the molecular weight of the drilling mud. So you can see in the shallow measurement, we're very close to the mud. So it's because the mud goes into the to an inch or two. When you go to 4 inch, you still have an impact, but your impact is a lot less. So you can see there is this variation in invasion of the drilling process, in fact. So these are very quantitative, in fact, quite well-established results. But there are many other more subtle effects that it's still in a research stage. If you look at details of these two-dimensional maps, the diffusion and T2, they are coming up different slope, right? You see these guys, they are pointing up, and this is going much more flatter, and they correspond to grossly different oils. So this last side is more asphaltene-rich oil, and this is simpler. This is mostly alkane. So the composition actually has an impact on these two-dimensional measurements. We don't have a full understanding of that, but that's part of the topic we're working on. There are other things that you can see as you, for example, if you take out the asphaltenes from the oil, then the red data is with asphaltene, the blue data is without asphaltene. So you can see the asphaltene is certainly making an impact. Or this is, you take a lower temperature in the waxy oil, and then you affect the diffusion greatly, you don't affect the relaxation. There are many other things that NMR can show you to reflect the molecular variation as the material changes. So those are actually quite much more current research topic. So now I want to go to another example, the shale. The shale is complicated. So shale, I'll point out one particular aspect that is complicated. That is the fluid, or we generally call it both the hydrocarbons and water, and there are many more categories. In the conventional, you have oil, you have some water, right? So that's pretty much what you have. Some flow, some not. But in unconventional, you have a much wider range of heavy or even solid organic materials, and that makes these measurements much more difficult. And we know that these, as a function of maturity, the composition of these organic material varies very significantly. So I'll flash up this kind of the result of a lot of the work. I'll show you a few examples that demonstrate these results. So in using this type of method, again a two-dimensional method, this is more T1 versus T2 map, then the different components appears to be able to separate. For example, kerogen and bitumen, these are not along this one-to-one line. This is a one-to-one line. They're moving upward. They're really significantly moving upward, and they have, and in these shale material, there's a lot of them. So that's very important to be able to quantify that. So I'll show you various examples. So these are a sample with, just as we received it. Now these are very low permeability samples, so they still have some liquid in them. So this is what you see. And when we saturate it with oil, then you can see there's a lot more signal in here. So we know this part is the oil signal, the original oil signal in that sample. And then these are most likely the bitumen, the kerogen signals. And this is done at a lower field that is compatible with the logging tool. They're typically much lower field. This is done at a much higher field, just trying to separate these signals more, and so that we can quantify them better. So this is done at 9 Tesla magnetic field, much higher field. But it's for the laboratory NMR. This is quite a standard instrument. So you see, there's a group of signal here. I mean, I label here. This is from the clay. I'll show you a reason for that. And the bitumens are here. The kerogens are here. If you have light oil, you will be generally following that diagonal line. So this is a couple of samples with different amount of clay, and you can see as you go higher in clay, this signal goes up quite dramatically. Right? So that's how we identify the clay signal. But one question is that, so the signal, oh sorry, let me go back to here. So these signals, they have very large, the T1 and T2s are very different. I mean, they're different by a factor of 1,000 or something. So why is that? This is, just from an experimental point of view, it's actually quite common. If you look at an oil, it always do this. So when the viscosity goes low, the T1 and T2 ratios go to very large. And from a physics point of view, this is actually well understood, that these relaxations are generated by the hydrogen atoms inside a molecule. When they rotate, the molecule don't sit still, right? They rotate. And when they rotate, they generate interactions, and these interactions causes the relaxation. This is well known. This is done at the very beginning of the NMR development, in the 40s. That when you vary the viscosity, the high viscosity, this is the T2, and the T1 goes into a minimum. So at a very low viscosity, like light oil, the T1 and T2 are very similar. Or like water, the T1 and T2 are very similar. But when you go to take something very heavy, then you could have a very large difference in the T1, T2. And that's what we have. As you go progressively to bitumen, to kerogen, your viscosity basically goes up tremendously. And that generates these T1 and T2 contrasts. And we can in fact take advantage of that, right? We know that the very high T1, T2 ratio, they are bitumen or they are kerogen, and we can take advantage of that to determine how well a reservoir might produce, right? Because the kerogen and the bitumen, they don't produce, right? They're basically the negative. They're reducing the permeability of the formation, and so you should not count them as the right organic material. It should be like the negative. So we have a simple empirical relationship that we put this index, reservoir productivity index. So we put the kerogen and bitumen at the denominator, and the oil would be the more desirable factors. So in fact, this is all empirical, but once you calculate the factor, this relates to quite well to how well the material produced. And then these techniques, because they are all based on the logging type of measurement, then you can actually use them. You can do, for example, this is very well identify what are the most productive pay zones in a reservoir. So let me see. So I guess I showed you a lot of how NMR might be used. It's a little random. I hope you might find the theme. There's many different applications that the NMR could help you. But the one downside is that the NMR itself is complicated. In particular, there are a lot of parameters you can vary. So often it requires an expert. When you want to use the NMR service, you hire an expert or Schlumberger sends someone over, talk to you and see how you should do it. That is very cumbersome, right? Most other measurement, you push a button, they will just do the measurement. And so what I want to talk to you about now, the next 5 minutes, is an approach that's based on statistics. That let the computer or let the tool, let the instrument to decide what are the parameters that they should use. Again, through some simple examples. Let's say we were talking about the T1 relaxation, right? We say the signal should recover like that. If you measure a few points, well, that's good, right? You measure that process. But that's when the sample happened to relax like that. If you use the same protocol, but the sample relaxes very quickly, well, only these two data will give you something useful, and then the others are already saturated. It doesn't tell you anything about the material. So how can you design a system that when this is the saturation, it will put all these variables in here, right? Trying to focus on what is the right parameter used. I'm sure this is not unique for any measurement, you will always do this. Say measuring temperature, there are many instruments that automatically change the scales and measure something more accurately. But for NMR, this hasn't been done before. And so this is a simple example. Let's say you have a signal that basically behaves like that, right? So you have, what you want to know is the measurement. You want to know what this A is, what the T2 is, right? The tau is your measurement parameter that you vary. Let's say if you have a data that's something like that. And you know that if you do one particular measurement, then you do not know all the features, and you have a big error bar, right? So I'm plotting roughly the error bar. How does the error bar goes as you do more and more measurement, right? Generally, this goes down. And for example, when you get down to about 20, well, you don't learn anything more. I mean, for example, you don't need to do more than 20 measurement in this. But also, you go 1 to 2. I mean, the 2 doesn't really learn much, right? So that's why the error bar doesn't go down very quickly. So what is the optimum way to do this experiment? Right. This is what we come up with. So you do some measurement, and what you want to do is you calculate the statistics of that one measurement. That is, what are the possibility of the A and the T2? I call it model, right? How many different models that will fit to your data? And then you generate a lot, right? You generate, let's say, 1,000 or 10,000 possible models that's consistent with your data. And then you take that model, because each model corresponds to a particular potential data set. And then you calculate that, and you calculate one more time that at what variable tau are these models mostly diverse. That means at that point we know the least. The measurement hasn't constrained anywhere on that for that particular variable. And then you determine, okay, that's where I want to measure, right? Then you do that, and then you just go in and do it again and again. So this is very simple, and there's no NMR here, right? This is for any measurement. This is what you want to do. In fact, after someone done the NMR PhD, you all think like that. You all do something, and then you know what you should do. I mean, it's actually not this algorithm. In a sense, reflect how we as an intelligent being think about how to solve the problem. So I'm just going through some of the examples. Before you take any data, right? You don't know anything about your sample. Everything in this plane is possible. If you take a first data point, well, you calculate. These are the possible solutions. And with that, each give you a curve, right? The first measurement was here, so you know they all have to match here, but they don't have to match anywhere else. And you calculate where has the maximum variance among all those solutions. Well, it turned out to be here. So, okay, my next measurement should be here. And then you go on, right? With 2, you can calculate again what are the ranges that you allow, then you can go on again. So the software is also quite simple. You just take a data. This is a command to take a data. And then this function tells you what your next parameter should be. I mean, in general, this is good for any experiment that you want to do. And here's a few examples actually running on the NMR device. And so the first point it measures here, and the second point it measures there. After the second point, it had reached the maximum or the accuracy limits, and you don't actually need to do more. And I just did a few more measurements, the blue point, just to show that these automated measurement is quite okay. And this is another example. It measures this first, and second one it measures over here. Once it got here, it realized this is decayed way too much, so it automatically put another point here. And you can go on and try these things. It's mathematically quite simple. And as long as you know how your signal should vary, or the other way of saying you have a forward model, then you can do all these statistics that are quite straightforward. So if we are working on how to implement this on an actual instrument, but I think it's very likely that there's quite some lot of benefits in doing this way. And the one thing is that you don't need an expert, right? You don't need a person to think how to do it. You just the computer basically duplicate how an intelligent person would decide how to do this. And this would be automation. So I hope I give you, I hope it's not too random sets of examples of what NMR might do, and especially in the geological material perspective, and some of the mathematics is actually quite interesting interesting from an actual automation point of view, but also it's not limited to the, I would say, limited to the NMR, and it's basically every complicated instrument could use this type of algorithm to automate the operation. And of course, this is not all my work. It's all done with my collaborators, of many people in Schlumberger, and over the many years. And I didn't talk much about the biological application, but the tissues are actually not too different from the rock. They're aggregates of cells. They have fluids in between. They're actually quite similar from the physics of fluid diffusion point of view, and it's actually a lot of common interest between biology and geological NMR. And of course, many people have taught me over the years a lot of the mathematics, geology, and chemistry was very, very enriching for me. And I certainly thank you very much for your attention.
Hi, Yiqiao. Thank you for the very fun and informative talk. So, anyone have questions? We have time for several questions.
Yes.
And what is the minimum strength that you have to apply the magnetic field? You mentioned the 9 Tesla. 9 Tesla is awfully high, and so you can go lower and then to have the same result.
Yeah, there's no limit. People do NMR at 0 magnetic field. You can. There's a signal noise issue.
Yeah, right.
Basically, let's say we do hydrogen, and there is like a frequency to this second power law that of the signal. So higher frequency is typically give you a higher signal, but there's many other issues. Like in the logging system, the magnetic field is not uniform, so it has a much broader bandwidth. And in that situation, it's not frequency to the second power. In fact, within a range, it's actually not very sensitive frequency. There are many things. We are right now doing NMR at half a Gauss. So you know what half a Gauss means, right?
About the Earth's magnetic field.
Yes.
Right.
So you can do NMR at Earth magnetic field, and so there's no intrinsic limit. It's just a signal noise, and depending on your application, how quickly you need the data. Yeah.
Back near the beginning, you had a nice slide that showed the diagram of the tool. And then on the right side, it showed a spot. And I think it would probably be helpful for this group, me in particular, if you could explain what that image is. I think it's probably magnetic field, something to do with contours of constant magnetic field.
Yes,
I know that magnetic field gradients are very important in localizing things, but this is the one. What exactly is displayed there in the black square? It just disappeared.
So this is a combination of the magnetic field profile and also the transmitter strength. So this is the color is actually the signal, the amount of signal emitting from each voxel. So like here are most of the signal coming from here, and the less signal coming from here. So but it is true that magnetic field contour also follows that shape. So yeah.
And when you're controlling the equipment to change the depth of investigation, are you changing the magnetic field gradient?
We
Are you
typically
looking at a
change-
different antenna frequency?
Yeah, we typically
Because I
change
think
the
this is an
frequency.
audience that would like to hear a little bit about the physics.
Okay.
Because you've done very well on the interpretation
Okay.
and on the statistical signal processing, but the underlying physics is really quite an interesting.
Right. So of course, when you make a magnet, let's forget about the details of the magnet. The magnetic field fall off, right, as you go away. So if you set to operate at a frequency, let's say we operate at 2 megahertz, and it typically is at a magnetic field about 500 Gauss. So basically, if this is, let's say this is 2 megahertz, then this is where the 500 Gauss is. There's a little bit of a bandwidth that we can specify, but that's only like a few Gauss. And if you say, I want to go to 1 megahertz, right, then you got to be farther away. So 1 megahertz is probably here. So you basically, by changing frequency of your instrument, you change where your sweet spot is, or how far you are from your instrument. So in fact, we exploit that property. This tool only operates, this is an older tool that operates at 1 frequency, but we have a different tool that operates at a series of frequencies, so you can see a range of, we call it slices. It's like slicing the earth and measure the signal within that slice. In the example I show you about the invasion, right, that is that particular tool that has multiple slices that you can excite. So that's why you can choose 1.5 inches and 4 inches. And compared to many other tools, that when we say it's 1.5 inch or 4 inch, we mean 1.5 inch and 4 inch. There's a thin slice around that depth. It's not integrating from 0 to 4 inches. So that's one practical benefit of NMR. We know where the signal comes from.
One more question.
So I think you, I think you just answered it, but you're sensitive to measurements at precise locations being 1 and 4 inches, and you're not averaging the properties over some range. And those are the only two distances at your localities that you're sensitive to measurements at. Can you go
no,
further?
But change frequency.
By changing frequencies, in the current system, we do set, I mean, you can change any frequency you want, but each tool has a software it don't allow to change some. So that tool that I show you, 1.5 and 4 inches, you can change anywhere in between. And typically we do 1.5 and 2.5 and then 4. So typically that's the 3 depths that we do.
But with conventional tools, you couldn't go 10 meters, 50 meters.
No, that's the tough one. So well, you can see, you only get signal from a very small spot. On the other hand, you receive noise from everywhere else, right? So everything gives you noise. So that is really the downside or the inefficiencies of the current tool design. Our sensitivity spot is too small. So the reason, well, I was saying that we are doing the earth field measurement, earth field NMR. The goal is, because earth field is uniform, right? Locally, not uniform in global sense, but give it a few meters, I'm pretty uniform. So I can excite several meters of the formation. So now I'm not selecting a slice, right? And my volume just goes up by thousands and probably even more. So that's that's the reason we're doing the earth field, and that's, if it's working, then we will be measuring much deeper into the formation. Exactly how deep? I don't know. Yeah.
Yeah, very quick question. Does the conductivity of the material really make some differences? For instance, the highly conducting thing, and so then you will have maybe some trouble.
Oh, good question. Good question. Very true. Very true. Conductivity is well, this is a EM, right? It's just EM. But if you're measuring an inch into the formation, well, at 1 megahertz, the penetration depth is probably like a meter for one inch. So it wouldn't affect this. for the Earth field measurement, where go down to 2 kilohertz, well, I think it would not affect anything for the open hole measurement. For cased well, you cannot irradiate out of the casing. So yeah, this would be an open hole only measurement.
So let's thank our speaker again.
All right.